Welcome, engineers. My name is Travis IQ, and today we have another networking and cybersecurity discussion. Today we're going to discuss routing concepts, and actually it'll be a practical routing concepts introduction, right? And one of the best ways to do that, to examine practical networking, is with a network simulation software, something like Cisco's Packet Tracer. So what you see behind me is Cisco's Packet Tracer. What we'll do is build a simplistic routed infrastructure, 2 routers, 2 switches, 2 PCs, and set up static routes between the networks, right, of PCs 1 and PCs 2 so that they can communicate. So let's build this thing. First off, we can drag in some routers. Let's see if we can't increase the size here. We can then drag in some switches. 2960s, for example, and some hosts. Generic PC host. Where have you gone, host? There you are. And a host. Right then, if we were to click on this router, what we'll actually see, if I want to zoom in here, is that there's really only one Ethernet interface. And it's a fast Ethernet interface, 100 by 10, so traditional Ethernet or fast Ethernet. And so what we actually need is an additional interface here, right? So what we need to do is drag in a module. We could drag in any number of modules, but if we drag in a WIC2T, that'll be serial. If I drag it in here, it's actually not going to let me do that, is it? No, it's not. It's not going to let me do that for a very specific reason, right? And the reason is the power's on. If you were to try and install a module into a router with the power on, it would not work very well for you either, right? And so what we need to do is turn this router off. We can then install a module. We might even want to install a cover. Interestingly enough, just a fun fact, if you were to install a cover, if you were to attempt to install a cover in the simulation environment, it would tell you cannot do that because the power's on, if the power were on. That's not how it works in real life, right? You could put a cover on the back of a router module slot without the power being off, right? Things to think about, though. This is just an interesting indication, right, that the simulation is not actually completely indicative of real life, right? So if you would say, hey, we simulated this and it didn't work identically as it would have in real life, that would be why. Let's turn her back on. If we go into the CLI and take a look, it's actually decompressing the image right now. We'll go ahead and get that started on the other router as well. Drag a WIC2T in here. We'll drag a little cover on just to be thorough, because that's what we are. We're thorough around here. If I go into the CLI, we're decompressing the image. I could actually fast forward this, and the image will be decompressed. I need to now connect my devices. My little connection slot. And a switch to a router connection is straight through. So we'll use a straight through cable and we'll go fast Ethernet to fast Ethernet, which makes a whole lot of sense. If you tried to go fast Ethernet to something like serial, that wouldn't work, right? Let's do it. Cable can't be connected to that port. Right, different port types. Just things to think about, right? We are engineers, which means we break things, right? If you've ever seen any of my other videos, I always end with engineer, break stuff, and have fun. Well, breaking things is having fun. And so we've already done that, what, 2 or 3 times already? And I'm sure we'll break something moving forward as well. I can go PC to switch. A PC to a switch is also a straight through cable, even though we do have auto sensing these days. Let's actually do this too. Slide this thing over here so you guys can see it, not right behind my head. Aha. Perfect. And then I said we were going to do serial, right, between the 2 routers, 000 to 000. We're going to make our lives a little bit easier here by showing all of the port labels, which we've already done. You can go into tools, options, preferences, always show port labels, and that will help you with this too. Just things to think about. And so you'll notice that we have our little red bulbs here and green bulbs, right, indicating that these links are active, right, and these links are administratively down. Right? This makes sense fundamentally because our switch ports are active, right, when we fire that switch up, and our router interfaces are administratively down by default. So we need to go in and configure some interface settings. We also need to give ourselves a plan. By plan, I mean a topology, right? So this is also a topology diagram for us, which is nice enough. And so what we can do is give some information about network address spaces so that we know which address ranges we're working with when we start configuring route statements. So we'll use the 192.168.1.0 address space /24, right? So it's a class C or 255.255.255.0. And we will use the 192.168.2.0 address space, another class C. And then we can use the 192.168.100. We'll make this a /30 because it's a point-to-point link. Great. Let's drag these things into some appropriate positions and get started. I would say probably the easiest thing for us to do in Packet Tracer is to configure the desktop IP addresses. So our desktop IP address will be 192.168.1.2. Right, the .1.1 is going to be our default gateway, our router address on the interface facing this PC. The subnet mask is going to be 255.255.255.0, and the default gateway will be the IP address of the router interface on this subnet, which is going to be the .1.1, so that you know. Okay. We can do it on PC1 as well. So PC1 is going to be 192.168.2.2 with subnet mask of 255.255.255.0. And the default gateway is now going to be 192.168.2.1, right? The .1 address in the 192.168.2 subnet. Again, I don't have to make it the first address in the subnet. It's just the most intuitive that way. And it's a pretty common addressing scheme to make your default gateway the first address in the subnet space. Now I need to address these interfaces. So let's pick FA00 here. We can issue the enable command and enter privilege exec. We can issue the configuration terminal to enter global config, and then we can configure an interface, right? FA00. Now we are literally configuring the FA00 interface. I can configure that interface with an IP address. And that IP address is going to be 192.168.1.1 with a subnet mask of 255.255.255.0. And I need to turn the interface on, right? The way I turn the interface on is the opposite of shutting it down. So no shutdown. And you'll notice this interface is now on, and this interface is converging. We should probably do the same thing over here. So we can configure FA00 on router 1 as well. Privilege exec, global config, interface FA00. It doesn't have to be identical, it just is in this case because we configured two identical sides, right? They're basically mirror images of one another. And the IP address is now going to be 192.168.2.1 with a subnet mask of 255.255.255.0. And I also need to not shut it down. Turn it on. Now actually I should probably make this the 100.0, shouldn't I? Now for the subnet connecting the serial interfaces. This is serial 00. I can actually just transition to that interface here, right, with this interface S00 command. I'm now configuring the serial 00 interface. I'm going to configure it with an IP address of 192.168 100.1. I'll start with 1 on the left side, and I'll go to 2 on the right side, right? Those are the only two viable addresses in the 192.168.100.0/30 subnet. We could talk about this. I'll talk about subnetting in another video, but for now, you should know that the .1 and the .2 address are the only available addresses in this space. Whoops. IP address would be more useful, wouldn't it? And I can turn this interface on. It's going to change it to temporarily down because the other side of the link is not up. S00. Is that right? We can check. I've got the port labels labeled. Yep. It is identical. Wow, shocker. I can give an IP address, 192.168.100.2 with a subnet mask of 255.255.255.0. And I can issue the no shutdown command. I could show my interfaces in a brief format, right? A simple format for me. And I can look at the IP addresses of each interface. 192.168.2.1, 192.168.100.2 is exactly what I thought. And they're both up and up. I can do the same thing here. Notice in the previous config, I went exit, exit. I can also go end. That'll bring me to privilege exactly the same with just one command instead of two. And I can go another show IP interface brief. And you'll notice now I have the 192.168.1 network with the .1 address being the default gateway, the router interface facing the 192.168.1 address space, right? And I have the 192.168.100.1 address, which is the IP address on the interface, on the serial interface, right? On that serial point-to-point link. Great. If I were to go to this PC, whoops, not the terminal, just command prompt and ping 192.168.1.1, I should receive responses. And in fact, I do. If I were to ping the 192.168.2.1 address, that would be this PC1 here, I will receive a destination host unreachable. This is indicating to me, right, that the device that is charged with forwarding this packet doesn't know where to send it. What device is charged with forwarding this packet? Router 0. Router 0 doesn't know how to get to the 192.168.2 network. Shocker. It's not connected to the 192.168.2 network, and we've given it no information regarding the 192.168.2 network. This is routing, right? Routers look at layer 3 header information, IP addressing information, and make forwarding decisions based upon their route table. Whoops. Show IP route. This device knows about these connected networks, 192.168.1 and the 192.168.100. This is very interesting, right? Because if this device knows about the 100 network and I ping the 192.168.100.2, I get responses. If I ping the 192.168.100.1.2, that's PC0 over here, I get responses, right? If I were again to ping 192.168.2.1, I get timeouts. This device still doesn't know about the .2 network, right? Let's think about some other concepts though, right? This router, router 0, can ping router 1. If PC0 were then to ping 192.168.100.2, I'm not going to get a destination host unreachable I'm not going to get any response. Ooh, that doesn't seem right. I just showed that router 0 knows how to get to router 1. Then why am I not getting a response? I'm giving you a moment to think here. Because router 1 does not know how to get back to router to 192.168.1, right? Router 1 knows how to get back to router 0, but router 1 doesn't know what's on the other side of router 0. So when an ICMP echo request comes from the 192.168.1 network into the 192.168.100.2 interface, the router goes, "Ah, yeah, that's me. I don't even know how to get to the 192.168.1 address." Then you'd say, well, didn't that come from router 0? Yeah, router 0 knows about the .1 space and the .100 space. What does router 1 know about? Router 1 knows about the 100 space and the 2 space. Yeah. So basically, for the same reason I can't get out to PC1 from PC0, I can't get from router 1 to PC0 either, because router 1 doesn't know about them. This is routing. This makes a whole lot of sense once we start thinking about it. So what do we need to do here? We need to add route statements. And the way that we do that, if I exit out here, is in global config. I need to enter the IP route command, and then I need to enter statements for the networks that are remote to router 0. What network is remote to router 0? The .2 network, right? So 192.168.2.0, 255.255.255.0. And this traffic, when router 0 sees it, must be forwarded out the serial 00 interface. Because that's the direction that that address lives in, right? Out the serial 00 interface. If I do a show IP route now, I have a static route for the 192.168.2 network, and that traffic should be forwarded out the serial 00 interface. Notice also the 192.168.100 network should be forwarded out the serial 00 interface. This makes a whole lot of sense. The only other traffic that's going to be destined for the 100 network is going to be 100.2, right? And so if I see traffic for the 100.2 address, then forward it out the serial 00 interface because it's going towards router 1, right? This, unfortunately, does not complete the discussion, though. So if I were to ping the 192.168.2.1 address, I no longer get a destination host unreachable because the host is reachable. I get no response. I get a timeout, right? Why is this? Because the host is responding, but router 1 doesn't know where to forward the traffic. What does that mean? What does that mean? Let's take a look. Let's roll the tape. So if I go to right, if I stop time basically and go into simulation mode, right, and I issue this ping command again, we see an ICMP echo request packet generated, and I move forward in time. Forward in time. Okay, spanning tree, thank you for that. Interrupting my forward in time. It's going. It didn't interrupt. It just was in between one of these forwards. DTP as well. Great. I guess I could filter this out too, but we'll leave it for now. Where have my ICMP echo requests gone? I was timed out. Why was I timed out? 192.168.2.1. Does this router know about the .2 network? Do show, I don't even need to do, show IP route. It does. Ah, it was timed out because I didn't ping this remote host. I pinged this interface here, right? I guess if I had interface labels on with like the numerical label for each interface, I didn't actually ping PC1. I pinged router 1's FA00 interface. Reminder, router 1 doesn't know how to get back to PC0. So we had the exact same problem, I just pinged a different address, right? I pinged a different interface. So I could actually show this problem more explicitly. I need to go forward in time a bunch. Forward, 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 forward. All right, it isn't timing out for me quick enough. Let's go back to regular mode and back to simulation mode. Whoops. I still didn't give it enough time. Fast forward in time. Fast forward. Now. Everything is timed out. What I wanted to do was to ping the .2.2 address. If I do this, I generate an ICMP echo request packet destined for PC1. If I forward traffic, if I go forward in time, router 0 knows how to get there because I added a static route entry. Router 1 knows how to get there. Because PC1 has the .2 address. Well, router 1 doesn't actually know how to get to PC1 yet because PC1 hasn't had any responses because I didn't actually ping 192.168.2.2. Right? I've never sent any traffic from PC0 to PC1. So what is router 1 doing? Router 1 is requesting the MAC address of PC1. How does router 1 do that? Router 1 does that with the address resolution protocol, right, to resolve MAC addresses from known IPs. This ARP response has been received. The .2.2 address is now cached. However, if we look, all of those ping requests were still timed out. Why were they timed out? They were timed out because router 1 still doesn't know how to get back to the 192.168.1 network. We're missing a route entry. Let's try this one more time. I need to enter a global configuration parameter, which is a route entry. I need to issue IP route. I'm routing for the 192.168.1 network with a subnet mask of 255.255.255.0, and I need to send it in the direction of S00. That's the exit interface. If I do show IP route, I now have a static route identifying the direction in which traffic should be forwarded to get to the .1 network. If I now issue a ping, to that remote host, I should receive 4 responses. And in fact, I do. If I were to issue a ping to the default gateway of the .2 network, which I should also be able to see, I do in fact see it. If I were to ping my default gateway, right, from PC0, its default gateway, I get responses. The only thing I see different is a TTL value difference, right? So the TTL is 255 when I am pinging a router with no hops in between. When this router forwards traffic, it decrements that TTL by 1. And when I receive an ICMP echo response, I actually get a TTL of 254, which is pretty interesting. We are going to expand upon this simplistic network example at a later date, but this is the fundamentals of routing, right? We entered 2 static routes for these remote hosts. We configured them with static IP addresses, and we confirmed that each of these hosts can reach their respective remote hosts. PC0 can reach PC1, and I should actually confirm the opposite direction as well. PC1 can ping 192.168.1.2. Whoops. Ping would be the ideal command here, would it not? And in fact, it can. I told you that it could ping PC0, and it in fact can ping PC0. I appreciate your time. As always, engineer, break things, and have fun. We'll see you next time.